So let's talk through the control section with the microcoded ROM added. We have the instruction at the bottom, and this is an 8-bit instruction. So now we can think about our instruction rather than the input to a combinational logic circuit, which then generates the sets and enables. The instruction is now pointing to an address, and that address holds all of the ones and zeros we require in order to produce the right values for the sets and enables. Now, we've also got the counter here up at the top. The counter is going to count here up to 16, but at the moment I've got it set up so it actually only does up to 7, and I've disconnected the rest of them. So I've left the wires hanging so that we can just reconnect them later on whenever we extend on this control unit in order to give us more complicated instructions. Now, the question is, how do we get to the right position in the ROM? Well, there's two factors we have to take care of. If you remember, whenever we first looked at introducing this ROM, we thought about the instructions as running along a horizontal line. So the instruction is part of the address. And then we had the position within that instruction, that is position 4, 5 and 6 of the execute cycle. And that 4, 5 and 6 is going to give us another 2 digits. So we're going to have 8 digits for our instruction, another 2 digits for the position within that instruction. So for example, if we had an ALU instruction, we would have the 8 digits of the instruction would give us a position, so that would be a starting position. And then we would have to offset that by a value of 1 or 2 in order to give us the positions for the 5 and 6 of the stepper. So the ALU instruction will have 3 values here for the execute. We have a value of 4, a value of 5 and a value of 6. And from these 3 here, we're going to generate the offset positions. So it will be the original position 4, and then it'll be offset by a value of 1, and then offset by another value of 1. And we get this here from this little circuit. And Timothy Morgan came up with this little circuit, and it's quite neat, and so we're just going to use it here. Now, whenever we extend it to more values in the stepper, we probably won't do it like this. We'll find a different method to do it. But that's for the future. So as it stands now, what happens is that we get our values here for our offset via this little combinational logic block here. And it's going to give us, if we were to zoom out here, you could see that if I was to, we had all zeros here. So when we start this off, it's going to reset it. If we start this off, when it gets to position 4, you can see we're at the first position here of the ROM. Now, whenever the clock goes on to this next one, we jump into the next position. Now, in this instance here, we won't actually jump into the third position. It's going to jump back to the beginning again, because we've got another little bit of circuitry here that we've not talked about yet, but we'll talk about just in a second. But this allows us to jump along to each of the individual positions that we require for each of the instructions. But remember, it's nothing other than just part of an address, and these 2 digits here are going to be the least significant bits, and the instruction set here is going to be the 8 most significant bits. So we're going to have 10 bits coming in. So that's why the ROM here, if we look at it, its address bit width is 10. So there's 10 bit address coming in. That's coming in here. And the output is 25 bits. So the 25 bits here are all of the output sets and enables. Now you'll note as well that it's not all entirely hardwired, because there were functions here, that is instructions, which required more than, say, 2 inputs. There were instructions with multiple inputs. So for example, if we had a jump if instruction, the jump if instruction was not only dependent on wouldn't only be dependent on that position within the ROM, there was also another input which we would have to take care of. So what it would mean is that whenever we thought about a ROM as being the instructions along the horizontal plane and the position within the instructions along the vertical plane, in effect we would have another input. Okay, so not only we would have our instruction here, we would have our input which would come from somewhere else. So if we were to design this right, we would almost have to think about it in terms of like a 3-dimensional ROM, and we're not going to go to do that. What we'll do is we'll leave the complicated instructions just hardwired. So this jump if instruction here is just left hardwired. Now, if you'll note here, I've put numbers along the side here. So I've put numbers 0, 1, 2, 3, 4 up to 11, 12, that goes up to 10, 11, that should be 11 and 12, 13, 14 up to 24. So we've got from 0 to 24, which is 25 outputs. And those are all connected to this output here from our microcoded ROM. Now, in order to get the correct values within the ROM, we're going to have to create a spreadsheet, or at least I've created a spreadsheet in order to do this. So let's go ahead and we'll have a look at that now. So all of the columns that we have here are going to be the outputs for the control unit. So for example, the number 24 was the bus add 1, and 23 is instruction address register enabled, and the other one here, 22, is the control enabled, which originally was our RAM enabled, accumulator enabled, and then we have the R0, R1, R2, R3 enabled, and we work all our way along, and we've got all of the outputs here to our ALU, and we've got all our sets along here and the sets for the register, and we've also got a stop and an end command here, and we've got the final output here in hex, and it's going to be a 7-bit hex number. Okay, because the 7 4s is 28, so that would be 28 altogether, but we're only actually using 25 of those. So this would be the kind of time consuming thing, and I've automated it a little, and you'll notice that down along the rows here we've got all of our instructions. So we've got our add instruction, shift right, shift left, so these are all of our ALU instructions, and then we've got our load and our store, data, jump register, jump address, and jump if. And you can see here we've actually got all the way down, and you can't quite see it, to 688 lines. So we've got 688 lines in our ROM in order to define all of the sets enables, the possible sets enables of our device. So it can get quite complicated, and you can see the reason why this complication has occurred, because we're going to have the R0, 1, 2 and 3, and R0, 1, 2 and 3 has to be able to write to the other to each of them themselves, and they have to write to the outputs as well, to the in effect what was the RAM. So it means that we're going to have to work every single combination of possible outputs in order to ensure that we capture everything. So for example, this ALU add, you'll see it's actually got 64 different values. And most of these values have been generated because we've decided to put the register sets and enables into the control unit ROM, so that they've been microcoded in, and that's why this is so complicated. And I've generated this here, and when I generated this for every code, I generated every single hex output, and all of these hex outputs in effect then have to be put, I put them all into a numerical order. And I also have, the reason why I put it in numerical order is that whenever you load it in to the actual ROM, there's going to be some of them that have got zeros, so they're all zeros, so they don't belong in that position. So you actually have to ensure that if there are numbers missing, then they're filled out with all zeros. So it was a little bit time consuming, but I went ahead and I generated this output, and you can see the actual output here. So this is the final output here, and again I've generated this within the Excel spreadsheet. Now don't worry too much about this if you're looking at it and thinking, oh, do I have to go ahead and do this? Well, you don't, because we're going to take the values for the sets and enables for the registers, and we're going to bring them back out so they're hardwired again. And if we do that, it means they simplify the values here within the within the microcoded ROM, and we'll do that on the next video. So I've gone ahead and generated that there, and when I've generated it, I've then loaded it up into this ROM block here. So I go edit contents, and you can see that they've all been loaded up, okay? And you can see as well that it's not necessarily a great way of doing it, because it means that the values here, the positions of all our ones and zeros for sets and enables, are determined by our code that we chose for our instruction set. Now, there was a very definite reason for choosing that code whenever we generated the 8-bit machine, and that code was then used in order to generate the required sets and enables through a combinational logic unit. But now we don't really, how we define the code is up to us now. We could decide that when we move on to a 16-bit machine that we're going to increase the number of registers, say from 2 to 3, or we may have from 4 to 8, and we may then decide we might want 8 registers to be used as data registers, and then another 8 for address registers. So we might end up with 16 registers. Okay, so we might want to write and move stuff in between them, and we don't need to bother with all of the combinational logic. We can redo our entire instruction set, and that is what we will be doing whenever we move on to a 16-bit instruction set. And we won't be able to, it won't be backward compatible, okay, but that won't matter, because we can still emulate the previous machine, the 8-bit machine, if we want to. So that's the direction that we're going to go in. Now, there's a few other bits and bobs within this design here that we can note, and that is that if we were, say, for example, to count, have a complex instruction, this complex instruction, let's say it took 16 of these counter positions, and then another instruction came along and it was a very simple instruction, then that simple instruction, again, we would have to count through all 16, even though it's maybe only going to use, say, position 4, it would then count through all the rest. So that would be a gross waste of the CPU clock and their time. So what we want to do is get to the end of the instruction. So if the instruction only goes to 4, then we want to finish it at 4. Okay, so that is, it goes to 4, and instead of counting 5, 6, it just goes back and it goes to the next fetch execute cycle. And we do that here with a stop command. Okay, so we have a little stop command here, and we put that stop command at the end of each of our instructions. So if you notice here, if I get to the instruction here, you'll see I've got stop, stop. So I put this stop command at the end. It tells it that that's us finished that with that instruction. So whenever we're finished with that instruction, it comes up to the counter, it goes into the counter and simply goes in here as an ST, which is just the same position as the reset. So it just goes in and resets the counter back to 1, so as it goes back to the fetch execute cycle. Now, there was one other little thing to note here within this unit, and that is that there's another little feedback here, because we don't want this stop instruction to occur at stage 4, because whenever we do that, you could work it out for yourself and have a little look at it, but you end up with a race condition, and we don't want that race condition to occur. So we only want the stop to occur after stages 4, which is okay, because that's exactly what we want to do anyway. So that's this circuit. Now, it's quite complicated to talk our way through, so why don't we just try and we'll go through just one simulation, a simple simulation, and we'll see it working. So we ensure that everything is reset by pressing the reset here, and we have to make sure that our ROM has got the values in it. So if you've saved this once, then it will still be there. So whenever you close Logisim down and open it back up, these values will still be held in this ROM. So the ROM is at the very bottom of our address space, and the very first instruction that comes along is going to be a jump instruction, and we're going to tell it to jump to the very first address in our RAM, because the RAM's where we're going to hold our program. Now, the program that we hold is simply a data instruction, so we're just going to put 0F into the register 0. And the final command is the stop, but the stop command's changed. Okay, I've changed this command to 3.5. It was originally CF, but I've changed it to 3.5. Okay, because CF was actually taking up one of our ALU instructions, a part of it. Okay, so another thing to note is that we have to ensure that the control unit has our microcode. Now, I'm calling this microcode, but we could actually call it nanocode for the stuff that's in here, which is something I'll get to maybe in the next video. So we've loaded up the ROM with the microcode or nanocode, and we're ready to get started. So whenever we get started here, again, we can just click through. So we're going to go through the fetch cycle. So it's fetched instruction 40, instruction address register is 1, and now the instruction address register has gone up to 8000, so it's jumped to now the position 8000. Okay, and that's going to get enabled. Okay, instruction 8000, and you can see here if you drop down into it, we're going to be looking at the value here. So we've gone to 8000, which is the very first location of this RAM block, and the first location is going to have the instruction for the data. It's a data instruction, which is 02, so it's gone and fetched this 02. So we head back in and we'll continue with this. So it's fetched 02, and what 02 is a data instruction, so it should grab 0F and then stick it into register R0, and there you go, it's stuck it into register R0. And then finally the next instruction will be the 35. There's the 35 here, which is the end instruction. Whenever it ends, we should get a little red light, and there's a little red light that tells us that it has ended. So that's a simple little program just to show you that it doesn't actually work. As I said, I'm not going to go through lots of other examples because this will change, and at the moment it's like a work in progress. So I did this video just to show you the how I progressed from one control unit version to the next one. So in the next version we will take the registers, and we will place the registers outside the microcoded control unit, and we will hardwire the registers, and you'll see how simpler the microcode design is after that. So that's all for this video. Thank you for listening. I'll get you in the next video. Goodbye.